This section is still technically part of Chapter 10, but I kind of put it on its own little section because complex numbers sort of introduces us to, well, a whole new set of numbers that we haven't worked with before. If you remember way back when we did factoring, we tried to solve something like x squared plus 4 equals 0, and I said you couldn't factor it over the set of real numbers because it was a sum of two perfect squares. You couldn't find a number that had opposite signs and still multiplied to be positive 4. But yet there is a solution to it using another set of numbers that we call complex numbers or sometimes imaginary numbers. What we do is we define I, which is the imaginary unit, as the square root of -1. And if we have a representation for the square root of -1, then we're able to solve that x squared plus 4 equals 0 using non-real or imaginary or complex numbers. One thing we got to remember as we do this is that I is no longer a variable. Now in this context, it has meaning as the square root of -1. So a complex number has the form of a plus bi. The first part is the real part. The second part is the imaginary part or the complex part or the non-real part. So if you have 2 plus 4i, the 2 is the real part, the 4 is the non-real part. And so we write it that way to distinguish which part is which. Do complex numbers like 2 plus 4i have applications? Sure. And look at your wall sockets in your house. They're all alternating current. Alternating current has a real part and an imaginary part. The same thing with any kind of electronics that have resistors. Resistors oftentimes have both real and imaginary components when you talk about the resistance that they provide in electrical terms. So there are applications of these complex numbers. They're not just something that mathematicians have dreamed up to add another chapter to the textbook or something. So what that really means then is that even the number 7 is considered a complex number because 7 you can write as 7 plus 0i. All real, no imaginary. In a pure imaginary part, there's no real number. So how do I write the square root of -1 as a complex number, 0 plus I or 0 plus 1i? Turns out that these complex numbers can be added and subtracted just like any other term, except, got to remember that I is not a variable. But the same type of basic rules apply. You would combine like terms together. You can multiply and divide them in similar ways. So let's do a couple of simple simplifications first. Suppose you want to simplify the square root of -16. You might think of it as the square root of -1 times the square root of 16. Well, the square root of 16 is 4. The square root of -1 we said was I, so 4i. For the square root of -32, we can break this down into the square root of -16, square root of 2. When possible, we pull the negative out. So that square root of -16 we said was 4i. Square root of 2. Now, if we want to write it in a plus bi form, then what we do is we write it as 4 square root of 2 times I. So we indicate that that is the imaginary part. For the third one, square root of -27. Biggest perfect square we can pull out is 9, except in this case, we're going to think of it as -9. Square root of -9 times 3. So the square root of -9 is 3i. If you think of it as square root of -1 times square root of 9, you get I times 3, which is 3i. Square root of 3, and that gives us 3 square root of 3 times I. Sometimes these things can't be simplified, like the square root of -15. Best I can do is I can pull out that I. Sounds painful. Pull out that I, and you're left with the square root of 15 times I. For the square root of -45, perfect square, 9 and 5. Let's pull the negative out with the 9. Square root of -9, 3i. We're left with the square root of 5. So let's write this as 3 square root of 5 times I. By the way, these imaginary numbers apply with square roots. They don't apply with cube roots because the cube root of a negative number already exists. We don't have to do anything with another number system to create it. All right, look at the square root of -50. So I get 3. I can break it down. Square root of -25, square root of 2. Well, the square root of -25, 5i. 3 times 5 is 15. So I got 15 square root of 2 times I. All right, we can add and subtract these numbers too. Right? When we add and subtract them, we do just like we've done before. We try to put like terms together. So here I've got a negative 10 plus 6. Negative 10 plus 6 is negative 4. Here I've got negative 4 plus negative 5, negative 9. So again, we're writing this in a plus bi form. So I can see the real part is negative 4, the imaginary part is negative 9. For the one underneath it, it might be helpful to drop those parentheses and distribute that negative sign. So I get negative 3 plus 2i. Negative negative 5 gives me plus 5. Negative negative 3i gives me plus 3i. So 5 plus a negative 3 is 2. And then 2i plus 3i is 5i. So there it is, a plus bi form. All right, for number 4, again, I might want to distribute that negative sign. So I got a negative 3 and a plus 2i. 9i plus 2i is 11i. But if I want to do this in a plus bi form, I better put the negative 3 first, plus 11i. So adding and subtracting is relatively simple. The one above it just says fractions, but it's the same idea. Multiplication and division require a couple of additional things. One of them is the recognition that these complex numbers actually go in groups of 4. So if I is the square root of negative 1, or if I am the square root of negative 1, no, I is the square root of negative 1, if you were to take this and square both sides, you'd get I squared on one side. The square root of negative 1 squared is just negative 1. So what I'm saying is that if you find an I squared is actually a real number. It's negative 1. I to the third is I squared times I. Well, I is the square root of negative 1 squared, so I squared is negative 1 times I. So I to the third is negative I. And then I to the fourth is I squared squared. So square that side, square that side. I to the fourth is 1. And then if you keep going, if you go I to the fifth, I to the sixth, I to the fifth is the same thing as I. I to the sixth is the same thing as I squared, which is negative 1. So these things repeat in groups, which means that when you write your answer, you should never have to use a power of I greater than 1. If you have an I squared, you replace it with a negative 1. If you have an I to the third, you replace it with a negative I. If you have an I to the fourth, you replace it with a 1. So all of your answers should not have higher powers of I than just I to the first. So how does this work? Well, I to the 25th, remember these things repeat in groups of 4. So I to the 24th, we know is just 1 because I to the 4th is 1, so is I to the 8th, 12th, 16th, 20th, 24th. So I to the 25th must be the same thing as I. The other thing you can do is this. Take 25 and divide it by 4. You'll get 6. What's your remainder? That's the power of I. So right there I have I to the first. How about I to the 7th? Subtract 7 minus 4 is 3. So I to the 7th is the same thing as I to the third. Oh, but wait, we said I to the third is negative I. So again, I was able to take those higher powers of I and reduce them back to some form of I to the first or a real number. All right, look at the next one. I've got an I to the 44th. Well, what happens if I take 44 and divide it by 4? I got 11 with no remainder. So that must mean I to the 44th is the same thing as I to the 4th, which is 1. So I to the 44th is entirely real. It's just equal to 1. All right, let's take a look at the first one up here. 4i times 5i. 4 times 5 is 20. I times I is I squared. But then I remember that I squared is equal to negative 1. So I get 20 times negative 1, negative 20. So 4i times 5i is a real number. It's negative 20. All right, look at number 2. Number 2, we're going to FOIL. 2 times 2 is 4. 2 times I is 2i. Minus 3i times 2 is 6i. Negative 3i times I is negative 3i squared. So this gives me 4 minus 4i minus 3, but I'm going to replace that I squared with a negative 1. So that gives me 4 minus 4i plus 3, 7 minus 4i. You might be able to skip a step as you get a little bit more comfortable with this and see negative 3i squared means negative 3 times negative 1, which is 3, and just add it from there. But when you're first starting out, you want to write everything out. All right, take a look at number 3. We have I squared of 3 and I squared of 8. I times I is I squared. Square root of 3 times square root of 8. Square root of 24. Well, I squared is equal to negative 1. Square root of 24 I can break down square root of 4 square root of 6. So negative 1 times 2 is negative 2 square root of 6. My answer is real, right? There's no complex part to it. All right, let's look at the one underneath it. Something interesting happens with number 5. If you FOIL this out, 6 times 6 is 36. 6 times negative 5i is negative 30i. 5i times 6 is positive 30i. 5i times negative 5i is negative 25i squared. The 30i's in the middle cancel out. This gives me 36 minus 25. Replace the I squared with a negative 1. So I get 36 plus 25, 61. We actually have a name for what we did in number 5. We called the second term, that 6 minus 5i, the complex conjugate. Remember we had conjugates, just the last couple of weeks, we were trying to get rid of radicals in the denominator. And so if we had like a 3 plus the square root of 5, we had a 3 minus the square root of 5, and that knocked out those square roots in the bottom. The same thing happens with imaginary numbers. If you want to get rid of the imaginary number, multiply by the complex conjugate, and so replace that plus sign with a minus or a minus with a plus, and then when you multiply them together, you're going to get a real number for an answer. And so that idea of a complex conjugate is going to come back soon. All right, take a look at number 4. Something interesting happens in number 4. And that is, look at that square root of 2 and that square root of 3 that are both under the square root sign. Let's see what would happen if I did it 2 different ways. What if I took the square root of negative 2, the square root of negative 3, and multiplied them together? But here, I wrote it as I times the square root of 2, and here I wrote it as I times the square root of 3. Right, pull out, make it a square root of negative 1, square root of 2, square root of negative 1, square root of 3, and so each one, an I comes out of it. So I times I is I squared. Square root of 2 times the square root of 3 is the square root of 6. Well, remember we said I squared was equal to negative 1, so my answer is negative square root of 6. What if instead of doing them separately, I decided to multiply them together first and do square root of negative 2 times square root of negative 3? Well, that would give me the square root of positive 6, which is not the same thing I got in the other way. The point is that when you end up with these radicals with negatives underneath them, you can't multiply 2 imaginary numbers together without simplifying them first, because then you don't get the same answer. Because then what happens is that negative part disappears. Negative 2 times a negative 3 is just positive 6, and you never end up with that negative sign popping out. It just goes away. So when we go back to our problem that we had that we were going to simplify, we're going to end up with a 2 plus the square root of negative 2 times 6 plus the square root of negative 3. So the first thing is we'll replace those square root of negative 2's and square root of negative 3's with their I representation. So I'll get 2 plus I square root of 2, 6 plus I square root of 3. And then we FOIL. 2 times 6 is 12, plus outside terms give me 2I square root of 3. Inside terms give me 6I square root of 2. Outside terms give me I times I is I squared times the square root of 6. Well, remember, we already did that here. So those outside terms just give me a negative square root of 6. And there's not much more I can do. I can have a 12 plus 2 square root of 3 times I plus 6 square root of 2 times I plus a negative square root of 6. And I guess the best thing I can do is I can group things together. So I want to group the real parts and the non-real parts. So here's my real parts. So 12 minus the square root of 6, that's my real part. What's the complex part? 2 square root of 3 plus 6 square root of 2, I. So this is in the form of A plus BI. It's just that the A's and the B's look kind of funny. 12 minus the square root of 6 for one of them. 2 radical 3 plus 6 radical 2 for the other one. All right, the last part is dividing complex numbers. When we divide complex numbers, we need to make sure that we rationalize the denominator. So in order to do that, we're going to multiply the top and bottom by the complex conjugate. I talked about that a little bit already. You replace the sign. So for an A plus BI, the complex conjugate is A minus BI. And when you do that, it makes the denominator real. Let's take a look at a few problems. Of course, they start simple, right? 5 over I. You want to simplify that. Multiply top and bottom by I. Gives me a 5I over I squared. Remember we said I squared is negative 1. 5I over negative 1, negative 5I. Right, so it cleans it up a little bit. Same deal over here. We're going to multiply top and bottom by I. That gives me a 9I on the top. 3I squared on the bottom, but remember that 3 times I squared we replace with a negative 1. So I get 9I over negative 3, negative 3I. All right, 3 and 4 both follow the same pattern in that I want to get rid of that I that's in the denominator. How do I do that? Multiply top and bottom by an I. Just remember when you do that, you're going to be doing some distributing. So multiply the top here by I, the bottom by I. So in the top, I get 7I plus 10 times, hey, are we getting good enough that we can multiply I times I and get I squared and go, hey, I squared is the same thing as negative 1. Down the bottom, 4 times I, 4I squared gives me negative 4. So I end up with a 7I minus 10 over negative 4. Now, if we want to write it in A plus BI form, we can actually separate these two things and make it negative 10 over negative 4 plus 7I over negative 4. Right, so I switched the order as I broke them apart. They already have a denominator in common. Separate them apart. And then we'll do a little simplifying. Negative 10 over negative 4 is the same thing as 5 halves. So I get 5 halves minus 7 over 4 times I. So now it's really in A plus BI form. The A is first, that's the 5 halves, that's the real part. The negative 7/4 is the complex part of the imaginary part. Right, let's do that for number 4. Let's run through that process again. Multiply top and bottom by I. So on the top, I get 6I minus 5 times I squared, but I squared is negative 1. Down the bottom, 2 times I squared, again, I squared is negative 1. So I get a 6I plus 5, right? Minus a negative 5 gives me a plus 5 over negative 2. A plus BI form, 5 over negative 2 plus 6I over negative 2 becomes what? Negative 5 halves. 6 over negative 2 is negative 3. So minus 3I. Real part is negative 5 halves. Complex part is negative 3. All right, last set of examples here. These are the ones I need a complex conjugate for. Down the bottom, I got a 2 plus I on the first one. If I want to get rid of a 2 plus I need to multiply top and bottom by 2 minus I. Remember, whatever you do to the top, you got to do to the bottom and vice versa. This way, we don't change the value of the question. All right, so 5 times 2 is 10, minus 5i plus 8i, right? 4i times 2 is 8i. So 8i minus 5i is 3i. Minus 4 times I squared, which is negative 1. Down the bottom, 2 times 2 is 4. Plus 2i minus 2i go away. Remember, this is the difference of squares pattern. And then you'll get a minus I squared, but we replace the I squared with a negative 1. Right, let me finish it up at the top here. This is a plus 4. So 10 plus 4 is 14. And down the bottom, 4 minus a negative 1 is 5. Right, so 14 over 5 plus 3/5 I. So there it is in A plus BI form. All right, let's take a look at number 6. For number 6, we're going to do the complex conjugate again. So I'm going to multiply top and bottom by 3 minus 5i. So up on the top, negative 4i times 3 is negative 12i. Watch the second part. Negative 4 times negative 5 is positive 20. And then I times I is I squared, which I replace with a negative 1. Down the bottom, when I FOIL this, 3 times 3 is 9. Outside insides go away. Minus 25 I squared is negative 1. So up on the top, I'm going to reverse my terms just to put them in the right order. So I get negative 20 minus 12i. Down the bottom, I get 9 plus 25, 34. When I go to separate these, I can knock a 2 out of top and bottom, so I get negative 10 over 17 minus 6 over 17i. Right? A plus BI form. The A is negative 10 over 17. The B is negative 6 over 17. And I'll bet you the 2 down the bottom work out similarly. Here, let me pull my other screen up and we'll do it where we have a little bit more space. So for number 7, the question was 3 plus 2i over 5 plus I. Right, we want to get rid of that 5 plus I on the bottom. So let's multiply top and bottom by the complex conjugate. So instead of a 5 plus I, a 5 minus I, because a difference of squares pattern, we'll wipe those out. Right, FOIL across the top, 3 times 5 is 15, minus 3i, plus 10i, minus a 2i squared, except I squared is negative 1. Down the bottom, 5 times 5 is 25. Outside, inside go away, because I'll get a negative 5i plus 5i. Just watch your signs here. Minus I squared. Well, I squared is negative 1. Right up on the top here, negative 2 times negative 1 is positive 2. 15 plus 2 is 17. 10i minus 3i is 7i. Down the bottom, 25 plus 1, 26. So I get 17 over 26 plus 7 over 26i. All right, we've probably done enough, but hey, there's only one more example left, so why not do it? Maybe this is one that you want to try on your own, and then come back in just a second, right? Pause the video, try it on your own, see how it goes, and then compare your answer against my answer, and see how we do. So I got a 4 plus 3i over a 5 plus 2i. Try it on your own, come back. All right, so let's see how we did. We're going to multiply top and bottom by 5 minus 2i. So 5 minus 2i on the top, 5 minus 2i on the bottom. FOIL it all out. 4 times 5 is 20, minus 8i, plus 15i, minus 6i squared, right? 3i times negative 2i gives me minus 6i squared, which really is plus 6. Down the bottom, the middle term should go away, so I'll get 25. Outside, inside go away, minus 4. And I replace the I squared with a negative 1. So up on top, I get a 26 plus 7i. On the bottom, 25 plus 4 is 29. So I can write my answer as 26 over 29 plus 7 over 29 times I. And there's my answer. And that's it. That's the end of our little intro to complex numbers.